This video follows on from the electrolysis topic that we did on molten liquids. So make sure you've watched that video first, or you're aware of how electrolysis is used to decompose molten ionic liquids. This video looks at how electrolysis is then used to make and in the manufacturing of aluminium. So let's look first of all, if you remember from last year or earlier this year, we made iron, and we made iron from its ore. Its ore was a compound primarily called hematite, which contains that compound on the board, iron 3 oxide, and we were able to obtain iron from its ore using the blast furnace. And using the blast furnace, we could primarily displace iron by carbon, because iron, as you can see here, is below carbon in the reactivity series. So we basically reacted iron oxide with carbon at high temperatures. We ended up with carbon dioxide and molten iron, which we removed down here in the blast furnace. Now, we can't unfortunately do that with aluminium. And I say unfortunately because this is, in terms of industrial manufacture of metals, the blast furnace is the cheapest way that you can do it. Unfortunately, however, aluminium, as you can see here, is above carbon in the reactivity series, and therefore cannot be displaced by carbon, and therefore cannot be made by the same method that iron is. And we therefore have to use electrolysis, industrial electrolysis. And the problem with industrial electrolysis is it uses huge amounts of energy, electricity, and electricity is very expensive. So it's a much more expensive process to make aluminium than it is to make iron. Now, aluminium is found in bauxite, that's its ore. So hematite was the ore for iron oxide. Aluminium oxide is found in bauxite, you need to know that. And the compound within that bauxite ore, the rock essentially, is aluminium oxide. That's the pure aluminium containing compound that you want to get to. We make it by electrolysis, which is a really, really expensive process because a huge amount of electricity are being used. There's also an added cost to this type of electrolysis because every so often we have to replace large, expensive carbon anodes. And we'll have a wee look at why we have to do that in a short while. Now, the other thing about this is that we have, like any electrolysis of any ionic compound, it has to be molten. So we have to melt the aluminium oxide. Initial attempts at this failed because the melting point of aluminium oxide is extremely high, and it was essentially just economically and physically almost impossible to get to the temperatures in a feasible manufacturing process to make the aluminium oxide molten. Now, we found a way around that in that we dissolve the aluminium oxide in a thing called cryolite, and that lowers the melting point of the aluminium oxide massively down to about 900 degrees Celsius from it was originally about 2000 degrees Celsius. Okay, so costs, as I said, there, electricity and replacing those anodes are very expensive. So the main raw material that we use here, I have already said, is bauxite. That's the rock on your screen now. Within that rock there is amounts of aluminium oxide called alumina. Okay, it is a white powder, you can see it on your screen now. That is the material that we want to get, and then we want to remove the oxygen from the alumina being, as I said earlier, pure aluminium oxide with a very high melting point of about 2000 degrees Celsius. And when we get rid of the oxygen from that, we can eventually get our pure aluminium, which has a huge and varied number of uses within our society. So things like step ladders, window frames, cars, making airplanes, buses, trains, aluminium foil that you use in your house, electric power lines, overhead power lines, cooking utensils, saucepans, etc. So, as I said earlier, we take this aluminium oxide, which melts at about 2000 degrees Celsius, which is way too high, makes the process way too expensive and extremely dangerous. We dissolve that into a compound called cryolite, which is on the board now. And when we melt those two together at about 900 degrees Celsius, that allows for the aluminium oxide to melt. And just to remind you that any ionic compound has to be melted in order for electrolysis to happen. The reason for that, okay, you should know anyway, is so that we have the free ions. In this case, we will have free aluminium ions, which will make their way to the cathode, and we will have free oxide ions, which will make their way to the anode, hence separating the aluminium oxide. Now, one of the big problems with this process, as well as it being super expensive, is, as you can see here, if you look at this rock contains a lot of sand and clays and materials beyond just the aluminium oxide that we want to get. That has to be got rid of. We can't magically get rid of that. One of the big environmental issues with this process is exactly that, getting rid of the waste from the bauxite. The waste is a thing called red mud. It's a highly toxic, very unpleasant material, and you can see here that it's basically pumped out into a big reservoir that's contained around the aluminium factory. Now, you can see it's a very unpleasant, you've got all this beautiful landscape around the aluminium processing factory, and then you've got this horrible what we call red mud reservoir right beside it, which is very destructive and very toxic on anything, and it has to be maintained and kept very, very carefully within that reservoir. But yeah, it's a big downside of the manufacture of aluminium from bauxite. So what happens here in aluminium formation in terms of the actual chemistry? Now, if you're doing foundation level, you don't need to know the actual chemical reactions that happen at the anode and the cathode. Everything else you need to know, but not the actual reactions. Well, if you remember from my aluminium oxide, I said that we would get aluminium ions when it's dissolved up in cryolite. So the aluminium ions will be attracted to the cathode, and when they go to the cathode, they will pick up 3 electrons, and there's where I will get my liquid aluminium. It's so hot in there, the aluminium remains as a molten liquid and is tapped out of the bottom of the case. It's a big steel electrolysis chamber that this is carried out, and we'll have a look at it in a few minutes. And that is the aluminium ions gaining electrons, and that is of course reduction. You will need to know that. Okay, and that happens at the cathode. So at the cathode, the aluminium ions gain 3 electrons to neutralize the 3+ charge on it and give you pure aluminium. Over at the anode then, the oxide ions that came from the aluminium oxide, they're attracted to the anode of course, and they have excess electrons on them, hence this 2+ charge, and they will turn into oxygen gas. Okay, and they will do that by each oxide ion here losing 2 electrons each to get rid of that 2- charge, and they will form oxygen gas. So the equation for that is down here, 2 oxide ions forming oxygen gas, and you losing your 4 electrons in doing so. And that's an oxidation reaction because electrons are of course lost. Okay. Now, this is a bit of a problem, this last equation, just put it back up again. These anodes and cathodes are made out of carbon graphite. Okay? Now, they are at 900 degrees Celsius roughly, and they are coming in contact with hot gaseous oxygen. So what do you think might happen whenever you get oxygen and carbon together at 900 degrees Celsius, roughly the temperature of a hot blue Bunsen burner flame, by the way? Well, this is what happens. The oxygen that's made, okay, will react with the carbon which is in the anode, and it will make carbon dioxide. That's a big problem because these graphite anodes are expensive, but over time the oxygen reacts with them, turns the solid carbon into gaseous carbon dioxide, and essentially corrodes away the surface and then the rest of these very expensive anodes. And that contributes to a large expense within this electrolysis process, in that you're starting to lose your anodes, and those anodes have to be replaced. So you're taking your solid carbon anode and you're turning it into gas. That's also an environmental problem because carbon dioxide is a greenhouse gas, and environmentalists would prefer that you do not put I think everybody would prefer you don't put excess carbon dioxide into the atmosphere because it's responsible for global warming. Now, let's have a look at the actual electrolysis chamber that this happens in. Okay, so we have our anodes that are dipped in like so, we just saw. Okay, we have a steel casing which wraps around another graphite In this case, that's the cathode. Okay, we have a tap, although it's not shown. We have a siphon here instead, but you often have a tap where the aluminium at the bottom is tapped out. And then you have in here your molten electrolyte, so that's your aluminium oxide with your cryolite mixed at about 900 degrees Celsius. And then your molten aluminium settles to the bottom whenever it's made. And see, they're siphoned out via that route, okay, on the left, or you often see, as I said earlier, you'll get a tap at the bottom where it's simply tapped out. Now, what often happens, what does happen is that at the top of this, where it's slightly cooler, you get an aluminium oxide crust. Now, engineers are quite happy for that aluminium oxide crust, I'll sort of draw it on here if you like, for that aluminium oxide crust to stay there. Now, that means that that aluminium in that, if it's a crust, isn't a liquid and can't be converted into aluminium metal. So they're quite willing to sacrifice that for a very simple reason. It acts kind of like an insulating blanket and it keeps the heat in, which means they don't have to spend as much money constantly heating the the electrolysis chamber here. So you can use that to your benefit, even though you lose a little bit of your aluminium. And if you keep the temperature up, everything stays molten and the conductivity of the aluminium oxide stays at a high level. So you have two things keeping the conductivity of the aluminium oxide high. You have the fact that you have that heat that's in there and that is allowed to sort of stay in there, if you like, with the crust, and you have the fact that it is dissolved in cryolite, which keeps those aluminium ions and oxide ions apart from each other and improves conductivity, as well as reducing the melting point of the aluminium oxide, which of course saves money. So you have various reactions that are going on. I've already sort of spoken about them. At the anode, the oxide ions are turned into oxygen, lose electrons. Okay, that is oxidation. At the cathode, you have the aluminium ions gaining electrons. Okay, that is reduction, gain of electrons. The overall reaction then is the aluminium oxide turning into aluminium and oxygen gas. And then you have that negative reaction happening at the anode, where the carbon solid gets converted into carbon dioxide through an oxidation process with oxygen. Now, why is aluminium such a popular metal? Well, it's got a huge amount of uses. Very, very versatile. Lots of these uses are around the fact that it's very light, it's very unreactive. Even though it's higher up in the reactivity series, it's very unreactive. The reason for it, I'll just tell you very quickly, is that aluminium, when it is sitting around, reacts very quickly with oxygen in the air and forms a layer on the outside of the aluminium of aluminium oxide. Aluminium oxide is extremely unreactive and basically acts as a protective layer against acids or water or oxygen or anything that the aluminium might come into place. It forms a very thin layer, but a very strong and unreactive and protective layer. You'll see lots of the uses here rely on it light. So for example, aircraft, low density but super strong. Tube trains, low density, really light but very, very strong. Okay. Aluminium foil, flexibility. Bicycles, again, very light but very strong, unreactive. You can leave them sitting around. Power lines rely on it being very, very light. So those are the power lines, not the ones that are in your little electrical cables in your house, but the big power lines that you see across the countryside. They have to be light, because if they weren't, okay, if you had power lines between two pylons and they were a heavier metal, they would simply sag over time. So aluminium is a good conductor but light. So you can see most of the uses there involve lightness, lack of reactivity, ability to conduct electricity and to conduct heat as well, of course, for saucepans. Now, recycling versus manufacture of aluminium is a bit of an issue. Recycling only costs 5% per tonne of what it costs to manufacture aluminium in the process that we have just seen. Okay, recycling only produces 5% of the carbon dioxide that's produced in that manufacturing process when the carbon anodes burn off with oxygen. Recycling does not produce red mud, which we saw earlier and talked about earlier. Very toxic, very environmentally unpleasant looking solution to a waste problem. Okay. Also, But the big problem is recycling of aluminium is only at about 25% at the minute. So despite big pushes to improve the recycling, 25% only of aluminium at the minute is recycled. So if we could get that way up closer to 100%, that would make a huge difference. Right, there are some questions then you can do here at the end, guys, of the PowerPoint, but you've got some in your notes as well. I'll put these up for you anyway. You can pause them and do them if you would like, okay? But that's the end of the video. Hopefully that allows you to understand the prep or the manufacture of aluminium from bauxite by electrolysis. Thank you. So pause the video, I'm going to move on. 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 Pause the video again, I'm going to move on. Pause it again. Okay, that's the end of the video, guys. Thank you very much. Hope that helps.